Hi, my friend. If you're new here, this is your quiet space to drift off while learning about the universe. Tonight, we'll explore how one tiny constant shapes everything, from atoms to the stars themselves. Just get comfortable, let your eyes grow heavy, and let the cosmos take care of the rest. Chapter 1: Max Planck and the Birth of the Quantum. At the end of the 19th century, physics looked almost complete. Many leading scientists believed that the great laws of nature had been discovered and that the remaining work would mostly consist of filling in small gaps. Classical mechanics described the motion of planets and falling apples. Maxwell's electromagnetic theory united electricity, magnetism, and light. Thermodynamics seemed to offer a deep understanding of heat, work, and energy. In this atmosphere of confidence, it was easy to imagine that the universe had already revealed most of its secrets. Max Planck did not share the arrogance of certainty, but he was very much a classical physicist. Trained in the traditions of German theoretical physics, he admired the second law of thermodynamics and hoped to base the whole of physics upon it. To Planck, the world was continuous, smooth, and governed by exact deterministic laws. He did not set out to start a revolution. Instead, he wanted to solve a very specific technical problem: how to describe the spectrum of light emitted by a perfect thermal object, what physicists call a black body. A black body is an idealized object that absorbs all radiation that falls upon it and re-emits energy with a characteristic spectrum that depends only on its temperature. When such an object is heated, it glows dull red, then orange, and eventually white as its temperature rises. Experimenters in Berlin and elsewhere had measured this glow with increasing precision. They could plot how bright the radiation was at each color or frequency. The resulting curve had a distinctive shape, rising from low frequencies, peaking, and then dropping off sharply at higher frequencies. Any successful theory of radiation had to reproduce this curve in detail. Classical physics tried and failed. Ludwig Boltzmann and others applied statistical mechanics, treating radiation as a gas of waves in a cavity. Lord Rayleigh and James Jeans used classical equipartition arguments to derive a formula for the energy distribution of electromagnetic waves. Their expression matched experiments at low frequencies but went disastrously wrong at high frequencies, predicting an infinite amount of energy in the ultraviolet part of the spectrum. This contradiction became known as the ultraviolet catastrophe. It was a sign that something fundamental in classical reasoning was broken, at least when applied to radiation in a cavity. Planck followed these developments closely. He also proposed his own formula, inspired by earlier work by Wilhelm Wien, which gave a good fit at higher frequencies, but failed at lower ones. For a time, there was a patchwork of partial successes and growing experimental accuracy, but no single theory that worked across the entire spectrum. Planck was deeply disturbed by this. He later wrote that he began to attack the problem of black body radiation as a matter of life and death for theoretical physics. If classical ideas could not survive this test, something deeper would have to be found. On an October day at the turn of the century, Planck discovered a function that fit the experimental data. He had been informed of precise new measurements by the experimentalists Heinrich Rubens and Ferdinand Kurlbaum. After an evening walk with Rubens, Planck went home and tried a different mathematical form that combined features of the earlier laws. To his amazement, the curve matched the data across all frequencies. He had the formula that would later be called Planck's radiation law. But at first, it was only an empirical success, a lucky curve fitting. Planck still needed a physical explanation for why this expression worked. Finding that explanation forced him to abandon one of his deepest convictions. To derive his law, Planck modeled the walls of the cavity as a collection of tiny oscillators, like countless microscopic springs and charges that could exchange energy with the electromagnetic field. He then turned to Boltzmann's statistical definition of entropy, which he had previously resisted. When he tried to apply the usual continuous energy assumptions, he could not recover his new law. In what he later described as an act of desperation, he made a bold, almost arbitrary assumption. Each oscillator could not take on any amount of energy smoothly. Instead, its energy could change only in small, discrete steps. Those steps were proportional to the frequency of the oscillator. The proportionality constant was a new fundamental quantity, later named the Planck constant and symbolized by the letter H. In Planck's hypothesis, energy was not exchanged continuously, but in packets, or quanta, each with energy equal to the frequency multiplied by this constant. He did not yet think of light itself as being made of particles. For him, the quantization applied to the energy of the oscillators that emitted radiation, not necessarily to the radiation itself. Still, the concept was radical. At a deep level, nature might be granular rather than perfectly smooth. Planck presented his result in December of the year 1900 to the German Physical Society in Berlin. He showed that, with this strange assumption about discrete energy levels, he could derive the exact black body spectrum that experimenters observed. He had introduced the first quantum theory into physics, although he himself did not fully grasp its implications. To him, the quantization rule was a mathematical trick that happened to work. Nonetheless, that presentation is now widely regarded as the birth of quantum theory. Over the next years, other physicists took Planck's constant more seriously than he did. Albert Einstein used the idea of energy quanta to explain the photoelectric effect, proposing that light itself was composed of individual packets of energy called photons. Later, Niels Bohr applied quantization to the orbits of electrons and atoms, explaining why atoms emit light at discrete frequencies rather than in a continuous smear. In each of these developments, Planck's constant appeared as the fundamental scale that sets the size of the quantum steps. What began as a desperate move to fix an awkward problem in thermal radiation grew into a new worldview in which microscopic processes are quantized. From a modern perspective, it is hard to overstate how transformative this was. The Planck constant is now woven into the very fabric of physics. It appears in the relations that link the energy of a photon to its frequency and the momentum of a particle to the wavelength of its associated matter wave. Underneath these technical roles lies a simple conceptual message. There is a smallest meaningful unit of action in nature, and that scale is set by h. Whenever the product of energy and time for a process becomes comparable to this tiny constant, quantum effects can no longer be ignored. The story of black body radiation also connects directly to the cosmos. The cosmic microwave background, the afterglow of the hot early universe, has a spectrum that is astonishingly close to that of a perfect black body. Satellites have measured this spectrum with great precision and found that it follows the Planck distribution almost exactly. This is a sign that the early universe was once in a state of near thermal equilibrium, filled with radiation whose behavior is governed by the same quantum law that Planck derived from his imaginary cavity. There is also a human side to this story. Planck was by temperament cautious and conservative. He did not seek philosophical upheaval. He wanted reliable universal laws, not strange discontinuities. Yet he was honest enough to follow the mathematics and the experimental facts where they led, even when they contradicted his expectations. He later described how painful it was to give up his belief in the absolute status of the second law of thermodynamics and to accept Boltzmann's statistical interpretation. The birth of the quantum was not a triumphant announcement of a new paradigm by a bold revolutionary. It was a reluctant step taken because the old view could no longer be maintained. Thinking about the birth of the quantum also offers a quiet form of reassurance. If the foundations of modern physics began with a crisis, they also began with patience, careful experiment, and a willingness to revise deeply held beliefs. As you listen to this story, you might picture Planck walking back to his home in Berlin in the cool evening, carrying the latest data in his mind, turning over functions and curves in his imagination. Somewhere in that quiet, he allowed himself to try something that did not fit his usual picture of the world. Out of that small departure came an idea that changed physics and shaped our understanding of the cosmos. For now, you do not need to hold all the details of that theory. It is enough to know that the universe, even at its most mysterious, proved to be understandable, step by step, by minds that were patient and attentive. As this day comes to a close, you can let the story of Planck and the birth of the quantum rest gently at the edge of your thoughts, like a distant glow on the horizon of the night. The same calm, ordered laws that govern black body radiation and the ancient light of the cosmos are at work all around you, steady and unhurried, as you allow yourself to breathe a little more slowly and let the weight of the day drift away. Chapter 2. The Planck constant, the smallest step in nature. To understand the quantum world, it helps to begin not with a particle or a wave, nor even with an atom, but with a single, extraordinarily small constant of nature. It is called the Planck constant, and although its symbol is simple and its numerical value tiny, it is the key that unlocks almost everything that makes the quantum universe different from the world described by classical physics. In a sense, the Planck constant tells us how grainy reality is when examined at its deepest levels. It does not describe a substance or an object, but a scale, a boundary line between behaviors that appear continuous and behaviors that reveal their underlying discreteness. In the same way that the thickness of a brushstroke sets the texture of a painting, the Planck constant sets the smallest possible texture of the physical world. The Planck constant appears in many branches of physics, but at first its role was subtle. When Max Planck introduced it, he did so reluctantly, almost as a computational convenience. He did not yet understand that he had placed a new cornerstone beneath all of modern physics. The constant he used represented a small quantum of action, a minimal package of energy linked to the frequency of an oscillator in his model of thermal radiation. But what he treated as a mathematical trick quickly revealed itself as a universal rule. When it appeared in the explanation of the photoelectric effect, in the theory of the atom, and in the emerging understanding of matter waves, it became clear that this constant was no mere adjustment. It was the scale at which classical intuition fails and the quantum description must take over. To appreciate what it means for the Planck constant to be the smallest step in nature, consider how energy behaves in the classical world. In classical physics, a system can absorb or release any amount of energy. The changes are continuous. You can heat a pot of water by a tiny amount or a large amount, and nothing in the theory restricts you to specific increments. The space of possibilities is smooth. Yet when physicists began studying atoms and radiation with finer and finer precision, this smoothness vanished. Atoms absorbed or emitted energy only in discrete increments. Radiation of a given frequency carried energy in packets proportional to that frequency. These behaviors were not approximations. They were fundamental. The Planck constant sets the scale of these packets. If you imagine a wave oscillating at a particular frequency, its minimum quantum of energy is the frequency multiplied by the Planck constant. Higher frequency radiation carries larger quanta of energy, and lower frequency radiation carries smaller ones, but none can be subdivided below the limit set by this constant. This does not mean that energy itself is chunky or granular in a crude mechanical sense. Rather, the ways by which nature allows energy to be exchanged and transformed follow rules that are irreducibly quantized. The Planck constant expresses the smallest allowed action, a quantity that blends energy and time into a single measure. Its smallness is what allows the classical world to look smooth at ordinary scales. But once you reach the domain of atoms and subatomic particles, the discrete structure of the quantum world becomes unavoidable. This constant enters physics again in the dual nature of light and particles. When particles such as electrons are associated with waves, the wavelength of those waves is determined by the Planck constant divided by the particle's momentum. Again, nature is not allowing arbitrary values. The presence of the constant ties wave-like properties to particle-like ones and ensures that the size of the wave cannot be infinitely small. This is part of the reason why electrons in atoms do not spiral into the nucleus, even though classical electricity and magnetism would predict such a collapse. The quantum behavior governed by the Planck constant forces electrons into stable standing wave states, creating the structure of atoms and thereby the structure of all matter. One can see the influence of the Planck constant not only in isolated atoms but in the behavior of entire fields. The vacuum of space, when examined through the lens of quantum field theory, is not empty. It is alive with fluctuations, virtual particles, and tiny vibrations that arise even in the absence of real particles. The energy of these fluctuations is set by the same constant. If the constant were significantly larger, the vacuum would seethe with unmanageable violence, destabilizing atoms and preventing the formation of complex structures. If it were much smaller, quantum phenomena would be too feeble to give rise to the rich tapestry of chemistry and condensed matter. The Planck constant is one of the parameters that makes the universe habitable, not through a mysterious fine-tuning, but through its role in creating a stable hierarchy of scales. In fact, the Planck constant, combined with other fundamental constants of nature such as the speed of light and the gravitational constant, defines natural units of length, time, and mass. These natural units represent the extremes at which our known theories begin to fail. The Planck length, an unimaginably tiny distance, is often interpreted as the scale at which space-time itself becomes subject to quantum fluctuations. The Planck time, The time light would take to travel that distance represents the limit of meaningful temporal intervals. These concepts are not merely theoretical curiosities. They appear in descriptions of the early universe and in attempts to build a theory of quantum gravity. When cosmologists describe the state of the universe at extremely early moments after the beginning of cosmic expansion, they often speak of the Planck era, a period so energetic and dense that classical spacetime breaks down and quantum geometry must take over. The Planck constant determines how easily quantum effects can be observed. Because the constant is incredibly small, everyday objects behave in ways that seem classical. The wave-like nature of a grain of sand or a moving car is negligible because the product of their momenta with the inverse of the constant produces wavelengths too tiny to detect. But when dealing with electrons, atoms, or molecules, their wavelengths become large enough to affect their behavior. Quantum interference, tunneling, and superposition all arise because the Planck constant places them within reach. The constant, in a sense, measures how quantum the universe looks at a given scale. It is tempting to imagine a universe with a different value of the Planck constant, but doing so shows how deeply embedded this constant is in everything from atomic structure to stellar processes. If the constant were significantly larger, quantum effects would dominate at macroscopic scales, making classical behavior rare. Objects would not have sharp positions or clear trajectories. If the constant were far smaller, quantum effects would retreat into an almost unreachable domain, and atoms would resemble miniature solar systems with electrons orbiting deterministically. Chemistry would lose much of its richness, and processes such as radioactive decay or fusion would unfold differently, perhaps not at all. The fact that the Planck constant has the value it does is not a sign of cosmic design, but a reflection of the delicate interplay of physical laws that shape our universe. Although the Planck constant is known as a physical constant, its meaning stems from a deeper insight that nature limits the precision with which certain pairs of quantities can be known or defined. This principle, later expressed by Werner Heisenberg, follows directly from the quantization introduced by Planck. The constant sets the scale of these limitations. They are not constraints of measurement technology, but intrinsic features of reality. When physicists speak of uncertainty at the quantum level, they are not speaking of ignorance. They are describing the fact that the universe does not assign exact values to certain pairs of properties simultaneously. This, too, is rooted in the same constant that Planck inserted into his radiation law at the start of the 20th century. In the century that followed Planck's discovery, the constant has become a foundation upon which quantum mechanics is built. Experiments continually reaffirm its role. Spectroscopy reveals atoms absorbing and emitting energy only in the discrete steps predicted by the constant. Superconductors show quantum interference effects on macroscopic scales, again governed by this same small unit of action. Devices such as atomic clocks rely on quantum transitions determined by the Planck constant, turning its microscopic influence into the most accurate measurements humans have ever achieved. Even the modern definition of the kilogram is tied to the Planck constant, linking our system of units directly to the quantum world. What began as a mathematical fit to a curve of thermal radiation turned out to be the measure of the universe's minimal granularity. It lies beneath every quantum leap, every interference pattern, every stable atom, every chemical bond. Without it, the universe would not possess the structures we know or give rise to the complexity that life depends upon. It is one of the quiet parameters that shape not just the physics of the world, but the possibility of the world itself. As you let this idea settle, imagine that the entire universe, from the smallest particle to the largest galaxy cluster, is shaped by a constant so small that it cannot be sensed directly. And yet, without it, there would be no stars, no atoms, no chemistry, and no consciousness capable of wondering why the universe is the way it is. In that sense, the Planck constant is a reminder of how the grand and the subtle are bound together. It shows how the vastness of reality depends on the smallest of limits, and how the quiet rules of the quantum realm ripple outward into the cosmic structures that fill the night sky. And perhaps, as you reflect on that delicate balance, you can allow yourself a moment of calm. The same constant that guides the behavior of electrons and the glow of distant stars also shapes the world that holds you now. You are woven into that structure, carried by the same gentle rules that govern the universe. As the day fades, you may feel the quiet reassurance that the cosmos, even in its most mysterious aspects, rests on simple, steady foundations that remain unchanged as you drift into rest. Chapter 3. The Planck Scale, where space and time break down. At ordinary human scales, space and time appear smooth, continuous, and sharply defined. We walk across a room and think nothing of assuming that distance has a clear meaning. We glance at a clock and treat each passing second as an identical unit, flowing evenly forward. Classical physics embraced this intuition, describing space as a continuous stage and time as a universal parameter that reliably marks change. Even in Einstein's relativistic picture, where time depends on motion and gravity, space-time is still a smooth, geometric fabric. No matter how far one zooms in, the theory treats space-time as infinitely divisible. But quantum theory introduces a different kind of structure, one that becomes unavoidable when we combine it with gravitation. When the principles of quantum mechanics intersect with Einstein's theory of gravity, they point to a profound conclusion. Space-time cannot remain smooth at arbitrarily tiny scales. Instead, at a scale defined by the Planck constant, together with the speed of light and the gravitational constant, the very notions of distance, duration, and geometry begin to lose their classical meaning. This region is known as the Planck scale. The Planck scale is not a place we can observe directly. No instrument can yet probe distances that small or energies that large. Instead, the scale emerges from thought experiments and theoretical reasoning. By combining the constants of nature in the appropriate way, one arrives at characteristic units of length, time, and energy that represent the regime where quantum mechanics and gravity must interact fully. These Planck units are exceedingly extreme. The Planck time, the time required for light to travel this tiny distance, is equivalently beyond everyday comprehension. These values are not arbitrary. They represent the scale at which any attempt to measure space-time with high precision would require so much energy that the measurement itself would collapse into a gravitational object. To understand why space-time breaks down at this scale, consider a simple mental experiment. Imagine trying to pinpoint the location of a particle with extreme precision. Quantum mechanics tells us that the more precisely we try to determine a particle's position, the more uncertain its momentum becomes. As we force the position uncertainty toward extremely small distances, the particle's momentum, and therefore its energy, increases dramatically. If the precision becomes too extreme, the concentration of energy required would be so great that the region would form a microscopic black hole. This black hole would hide any information about the particle's location behind an event horizon. The attempt to define the particle's position would fail, not due to technological limitations, but due to the fundamental laws of nature. This interplay between quantum uncertainty and gravitational collapse suggests that below a certain threshold, the concept of distance becomes ambiguous. The Planck scale is therefore not just a region of extreme smallness, but a boundary to the applicability of classical geometry. It signals the point where space-time itself may fluctuate, where the smooth manifold described by general relativity gives way to something far more irregular, perhaps even discrete. Physicists have proposed different interpretations of what space-time might look like at the Planck scale. One idea is that space-time becomes foamy, with constantly appearing and disappearing microscopic black holes and distortions. These fluctuations are sometimes called space-time foam. They arise because quantum mechanics allows energy to appear spontaneously for a brief moment, and gravity acts upon that energy, distorting space-time. Another idea comes from approaches such as loop quantum gravity, which suggests that areas and volumes may come in discrete units, like the pixels of an image, but incomparably smaller. In some formulations, space is woven from tiny quantum threads whose collective behavior reproduces classical geometry at larger scales. String theory offers a different perspective. It proposes that at extremely small distances, the concept of a point particle breaks down and is replaced by tiny vibrating strings. These strings have a natural length scale, which is typically associated with the Planck length. In this view, space-time cannot be probed below this scale because any attempt to localize an object more precisely stretches the string or excites higher vibrations, effectively preventing the formation of arbitrarily sharp spatial features. In all these approaches, the same idea appears again. The Planck scale is the frontier where space-time stops behaving like a continuous surface and starts behaving like something more fundamental, something not yet fully understood. The implications of this boundary are profound. They affect how we think about the earliest moments of the universe. According to cosmological models, the universe expanded from an extremely hot, dense state. If we extrapolate Einstein's equations back in time, the density and curvature grow without bound, culminating in a singularity. But singularities are a sign that a theory has reached the end of its domain of validity. The Planck scale signals the point at which classical relativity must give way to a quantum theory of gravity. Before roughly 1 Planck time after the beginning of cosmic expansion, space-time itself may not have existed in any classical sense. Instead, the universe may have been governed by a quantum state with no definite geometry. Only after emerging from the Planck regime could a smooth space-time appear. The Planck scale also plays a key role in discussions of black hole evaporation. According to theoretical models, black holes lose energy through radiation and shrink over time. As they approach the Planck mass, their behavior becomes uncertain. Some models predict that black holes may evaporate completely, leaving behind pure radiation, while others propose that a stable remnant may persist. In either case, the Planck scale acts as the endpoint of classical descriptions of black holes. When the mass reaches this threshold, quantum gravitational effects take over. Another fascinating consequence of the Planck scale involves the limits of measurement. Quantum mechanics already restricts how precisely we can know pairs of quantities. But when gravity is added to the picture, a deeper limitation arises. Any device capable of measuring extremely tiny distances would, by necessity, require energy so concentrated that it might collapse into a black hole. In this way, the Planck length becomes not merely a practical limit, but a fundamental limit. Theories that suggest space-time is discrete interpret this limit as a sign that distances smaller than the Planck length do not exist at all. Much as there is no meaningful sense of distance smaller than the spacing between atoms in a crystal lattice. Even with all these ideas, physicists are still searching for the correct description of physics at the Planck scale. Various approaches to quantum gravity continue to develop. Loop quantum gravity has produced models in which space-time is quantized into small discrete units. String theory has offered insights into how different forces might unify at extremely high energy. Other proposals include causal set theory, where space-time is treated as a collection of discrete events linked by causal relationships, and asymptotically safe gravity, where the behavior of gravitational interactions changes in a controlled way at extremely high energies. Although these theories differ in technique and interpretation, they share the belief that classical spacetime cannot be the final description of reality. What is remarkable is that all this theoretical richness arises from combining the Planck constant with Einstein's framework. Without quantum mechanics, space-time remains smooth and continuous. Without gravity, quantum effects occur on a fixed background geometry. It is only their union that forces us to confront a regime where neither description alone is adequate. The Planck scale sits precisely at that intersection. It is a reminder that even the most familiar features of the universe, distance, duration, geometry, depend on deeper principles that are still being uncovered. Though humans may never directly probe the Planck scale with experiments, its influence is felt throughout physics. It defines the boundary of our current theories, shaping our expectations of what a future unified theory might look like. It anchors the earliest eras of cosmic history and sets the conditions for the formation of spacetime itself. It challenges our intuitions about motion, locality, and measurement. And it serves as a compass, guiding physicists toward the theory that might ultimately describe the quantum foundations of gravity. As you let these ideas rest in your mind, it may be humbling to think that the universe, vast and ancient, is shaped by behaviors that unfold at scales far too small for direct observation. The Planck scale lies forever beyond reach, yet it guides the structure of everything you see. It is the boundary where space-time dissolves into something more fundamental, the threshold at which the universe hints at its deepest rules. In that sense, the Planck scale reminds us that reality is layered, mysterious, and far richer than everyday perception suggests. And as you reflect on this boundary between the knowable and the unknown, perhaps you can feel a quiet sense of connection to a universe whose deepest foundations whisper beneath every moment of your life, steady and patient, inviting contemplation as the night becomes still. Chapter 4: Quantum Jumps, the discrete heartbeat of the universe. In the world of everyday experience, change feels continuous. A shadow moves smoothly across the ground, a clock hand sweeps forward without visible breaks, and a dimmer switch brightens a room in steady gradations. Classical physics embraced this intuition, describing energy, motion, and light as phenomena that vary gradually. But at the scale of atoms, that continuity dissolves. There, the universe behaves according to rules that permit only sudden changes. These abrupt transitions, quantum jumps, form the backbone of quantum mechanics and reveal a world whose deepest workings unfold in discrete steps. The earliest clues came from spectroscopy. When heated gases emit light, they do not produce a smooth spectrum of colors, but a set of sharp lines. Each element glows with a pattern so precise that it acts like a cosmic signature. For years, these lines were mysterious. Classical theories predicted that atoms should radiate at all possible energies, yet experiments revealed only very specific ones. The idea that atoms might have internal quantized energy levels gradually emerged from this puzzle. The breakthrough came with the proposal that electrons in atoms cannot possess arbitrary energies. Instead, they occupy discrete energy states. When an atom interacts with light or heat, an electron may move to a higher state, but it cannot linger between levels. When it returns to a lower state, it emits a photon whose energy corresponds exactly to the difference between the two levels. That photon becomes a bright line in the spectrum. Because the energy levels are sharply defined, so is the emitted light. These transitions, the jumps, happen abruptly. Between them, an atom does not slide toward emission. It waits, existing in a stable state until, unpredictably, a photon appears. This suddenness puzzled early physicists. It seemed to contradict the continuity of classical physics, but experiments left no doubt. Atomic change is quantized. Niels Bohr's early model captured this behavior. Though later replaced by more sophisticated quantum mechanics, the model introduced the idea of stationary states and discrete jumps between them. In modern theory, electrons are described not as orbiting particles, but as wave patterns around the nucleus. Each allowed energy corresponds to a particular standing wave. The transition from one standing wave pattern to another is the quantum jump, and it remains sudden because the wave functions themselves are distinct. No physical state exists between them. The consequences of these transitions reach far beyond isolated atoms. Every color we see arises from electrons jumping between energy levels in molecules and solids. The green of a leaf, the red glow of a sunset, the blue shimmer of a flame, all are consequences of quantum leaps. Astronomers decode the chemical composition of distant stars by observing the spectral lines produced by these jumps. Even the cosmic background radiation retains traces of quantized processes in the early universe. In this sense, quantum jumps are woven through the entire cosmos, translating microscopic behavior into macroscopic appearance. Quantum jumps can also be observed directly in modern experiments. With a single ion trapped in an electromagnetic field, researchers see bursts of emitted photons occurring at irregular intervals, a direct record of spontaneous decays. The ion remains dark until the moment of a jump, brightens during emission, then falls dark again. This behavior is not noise or instrument error. It is a single atom tracing out the probabilistic heartbeat of quantum mechanics. Each burst marks the instant when the atom leaps to a lower state. The randomness of these events is not due to hidden disturbances we cannot measure. It arises from the fundamental structure of quantum theory. One can calculate the average rate of emission for a large group of atoms, but not the moment any single atom will jump. Nature permits only probabilities. For a single quantum system, the timing is irreducibly uncertain. This uncertainty is connected to another cornerstone of quantum mechanics, superposition. Before a jump occurs, the system may exist in a mixture of the excited and ground states. The wave function describes a set of probabilities rather than a definite condition. The emission marks the collapse of that superposition into a single outcome. This is why quantum jumps are not merely energy changes. They are changes in the very definition of the system's state. What was once a cloud of possibilities becomes a single reality at the moment of transition. Quantum jumps also appear beyond atomic physics, particularly in nuclear processes. Radioactive decay occurs when an unstable nucleus suddenly transitions to a more stable configuration, emitting particles in the process. Like atomic emission, the decay is unpredictable for any individual nucleus, but predictable in large samples. The same mathematics that describes atomic jumps governs nuclear decay rates. These jumps help power the interior of planets, warm the Earth's crust, and generate the neutrinos that stream constantly through our bodies. In molecules, quantum jumps underpin chemical reactions. When bonds break or form, electrons rearrange themselves through transitions between quantized states. The vibrational and rotational energy levels of molecules are also quantized. Infrared spectroscopy, which measures these molecular energy differences, reveals discrete absorption lines caused by energy jumps among vibrational states. Even the stability of matter arises from these quantized behaviors. Without discrete energy levels, electrons would spiral into nuclei or absorb energy continuously until atoms collapsed or exploded. Quantum jumps, paradoxically abrupt, are the reason matter is stable. Modern quantum technology uses these jumps in remarkable ways. Lasers rely on stimulated emission, a process in which an electron already poised to jump is triggered by an incoming photon to emit another photon of identical energy. This chain reaction creates an intense, coherent beam of light. Atomic clocks, the most precise timekeeping devices ever built, measure the frequency of specific quantum transitions in atoms, such as cesium or ytterbium. Because these transitions occur with exquisite regularity across countless atoms, their collectively averaged jumps define precise intervals of time. Despite the success of quantum mechanics, the nature of quantum jumps was debated for decades. Some early interpretations questioned whether the discontinuity was physically real or merely a reflection of limited knowledge. Today, experiments strongly support their reality. Controlled observations of individual atoms and superconducting qubits capture jumps in real time. The transitions appear sudden, statistically random, and quantized, confirming the core predictions of quantum theory. Quantum jumps also challenge our understanding of time. At the classical level, time seems continuous, a smooth parameter used to describe motion. But jumps reveal processes that do not evolve gradually. Instead, the system follows a smooth evolution of probabilities until a sudden transition occurs. In some interpretations, the jump itself is not part of time's continuous flow, but a kind of event that resets the system. This raises deep questions about whether time at the quantum level is fundamentally different from the time we experience macroscopically. There is also a conceptual tension between the smooth evolution of the quantum wave function and the abruptness of collapse. Quantum theory contains two types of processes: continuous evolution when the system is unobserved, and discontinuous jumps when an interaction produces a definite outcome. Much work in quantum foundations explores how these two modes coexist and whether the boundary between them is sharp or gradual. No interpretation changes the observable fact. Quantum jumps are real physical events, and they structure the behavior of the microscopic universe. Reflecting on these ideas, it becomes clear that everything in the universe, from the colors of stars to the chemistry of life, is built from sudden steps. We do not notice these transitions because they happen at scales far removed from everyday perception. But without them, the world would lack structure, contrast, and stability. Even the warm glow of a candle is a symphony of electrons leaping between states, each jump contributing its tiny flash to the whole. As you let these thoughts settle, consider the quiet strangeness of living in a universe made from leaps. You move through your day in continuous arcs, yet beneath that smoothness lies a deeper world where change arrives in quantized pulses. The fabric of existence is stitched from abrupt transitions, tiny decisions of nature that happen without warning. And somehow, out of those countless jumps emerges the steady rhythm of your own life, your breath, your heartbeat, your awareness. In that sense, the quantum world is not separate from you. Its discontinuous steps form the foundation upon which your continuous experience is built. And as you reflect on this delicate balance, the leaps beneath the flow, perhaps you can feel the quiet reassurance that even abrupt changes belong to a larger harmony, one that holds you gently as the day fades into evening. Chapter 5: Planck's Constant and the Dual Nature of Light. Light has always held a special place in human understanding of the universe. Long before physics became a science of equations and measurements, people sensed that light was something fundamental. It revealed the world, carried warmth, and marked the boundary between day and night. As scientific tools advanced, light became one of the first natural phenomena to be probed with precision. And each time physicists looked closer, light revealed a new layer of complexity. In the modern era, much of this complexity is tied to a single idea: that light behaves as both a wave and a particle, and that this dual nature is controlled in a precise way by the Planck constant. Before the quantum revolution, light was widely understood as a wave. Experiments had shown that it could diffract, interfere, and spread out in characteristic patterns. Thomas Young's double-slit experiment demonstrated that light passing through two narrow openings produces a striped pattern on a screen, a hallmark of wave behavior. Waves cancel and reinforce one another. Particles do not. This wave theory fit well with the emerging understanding of electromagnetism. According to Maxwell's equations, light is an electromagnetic wave, a ripple in the combined fields that permeate space. Its speed, amplitude, and wavelength could be predicted with remarkable accuracy. By the end of the 19th century, the wave description of light seemed complete. But discomfort appeared in the details. Certain phenomena refused to fit within the wave framework. One of the most puzzling was the photoelectric effect. When light shines on a metal surface, electrons can be ejected. Classical theory predicted that the rate of electron emission should depend only on the brightness of the light, because brighter light carries more energy in its waves. Yet experiments showed something different. If the light's frequency was too low, no electrons were emitted, regardless of intensity. Only when the frequency rose above a threshold would the metal release electrons, and the energy of those electrons depended on frequency, not brightness. Classical waves could not explain such behavior. The resolution came from a bold reinterpretation of light's nature. To explain the photoelectric effect, Albert Einstein proposed that light's energy does not spread out continuously, but comes in packets, which he called quanta. The amount of energy in each packet is proportional to the frequency of the light, and the constant of proportionality is the Planck constant. High-frequency light carries quanta with more energy. Low-frequency light carries less. If the energy of a quantum is below the threshold required to eject an electron from the metal, no emission occurs, no matter how many quanta strike the surface. This was the first clear demonstration that light sometimes behaves like a particle. Quantum theory therefore forced a new concept into physics: the photon. A photon is not a particle in the classical sense, like a tiny grain or bead. Rather, it is a discrete quantum of the electromagnetic field, a localized packet of energy that travels through space. It does not have mass, but it carries momentum and energy, and its energy is set directly by the Planck constant. This was not a minor adjustment to wave theory. It changed the foundations of physics. One might imagine that light must be either a wave or a particle, but quantum mechanics shows that such a dichotomy is too simple. Light exhibits both behaviors depending on the context. When it propagates, light spreads out like a wave. When it interacts with matter, it transfers energy like a particle. And the switch between these behaviors is not arbitrary, but governed by the Planck constant, which sets the size of each quantum. The dual nature of light is not a mere philosophical statement. It is observed in countless precise experiments. In the double-slit experiment, even when light is emitted one photon at a time, the interference pattern still appears. Each photon lands on the screen as a single spot, like a particle, but after many photons have arrived, their collective distribution forms a pattern of bright and dark fringes. It is as though each photon travels as a wave, explores multiple possible paths, and then lands as a particle. The Planck constant ensures that these wave aspects remain detectable. If the constant were vastly smaller, light's particle aspects would dominate and interference would be nearly impossible to observe. If it were larger, the wave nature would become overwhelming, and the microscopic behavior of matter would look very different. At the atomic scale, the dual nature of light becomes even more apparent. When an electron in an atom transitions to a lower energy level, it emits a photon. The energy of that photon is precisely defined by the difference between the two levels. There is no flexibility in the amount of energy the photon can carry. This rule, too, reflects the Planck constant. Because atomic energies are quantized, and because photon energy is proportional to frequency through the constant, atomic transitions act like a finely tuned mechanism for producing and absorbing light. The spectra of stars, nebulae, and galaxies all owe their structure to such quantized processes. When astronomers analyze starlight, they are reading a language written in the dual nature of light. Quantum electrodynamics, the theory that describes how light interacts with charged particles, is built entirely upon these principles. In that theory, light is treated as a quantum field with excitations, photons, that carry energy between particles. At the same time, the propagation of the electromagnetic field displays wave-like features. The Planck constant appears in the equations that govern these behaviors, determining the scale at which quantum fluctuations occur. According to this theory, even in empty space, the electromagnetic field fluctuates. These fluctuations arise because quantum mechanics forbids the field from being perfectly still. The vacuum is filled with tiny transient disturbances, virtual photons, whose behavior is determined by the same constant that governs the emission of real photons. This restless nature of the vacuum also produces measurable effects. For example, two uncharged metal plates placed extremely close together feel an attractive force, an effect that arises from differences in the quantum fluctuations between the plates and outside them. This is known as the Casimir effect. Such observations confirm that the quantum nature of light extends far beyond ordinary illumination. It shapes the structure of empty space itself. In the modern understanding of the universe, light's dual nature plays critical roles in cosmology as well. The cosmic microwave background, the faint glow that fills the universe, is composed of photons released when the early universe cooled enough for electrons and nuclei to form neutral atoms. These photons carry information about the universe's density fluctuations at that time. Their behavior is partly wave-like, producing patterns of oscillation on cosmic scales, and partly particle-like, carrying discrete energy. The Planck constant sets the scale of their energy and therefore influences how the early universe evolved. The dual nature of light also influences thermodynamics at the quantum level. In a hot object, such as a star or a heated filament, atoms constantly emit and absorb photons. The statistical behavior of these photons determines the spectrum of thermal radiation. This spectrum, which Max Planck originally sought to explain, is governed by the Planck constant. Without quantization, classical theory predicts an infinite amount of high-frequency radiation, a result completely at odds with reality. The Planck constant resolves this by limiting the number of high-energy photons, shaping the radiant energy of all hot bodies. Every glowing ember, every warm star, every thermal lamp owes its color and brightness to this quantum limit. It is remarkable that the Planck constant serves as a unifying factor linking these diverse behaviors. It ties together how photons are emitted, how waves interfere, how fields fluctuate, and how atoms interact with light. Although the constant is extremely small, its effects are everywhere. It ensures that light is neither fully wave nor fully particle, but something richer and more subtle. If classical waves were the whole story, atoms could not produce discrete spectra. If particles alone defined light, interference would not exist. The universe as we know it would be structurally impossible. This duality extends beyond photons. Matter itself displays wave-particle duality. Electrons, neutrons, atoms, even large molecules exhibit interference in controlled experiments. Yet photons remain the clearest expression of the dual nature, because they arise from the interplay of fields and quantum energy packets in its purest form. The more we learn about the fundamental workings of light, the more it becomes clear that the boundary between waves and particles is not a boundary at all. It is a feature of our macroscopic interpretation. At the quantum level, light simply follows the rules defined by its field and by the Planck constant. Whether we observe wave-like or particle-like behavior depends on the measurement we choose, not on a hidden identity that light must maintain. The Planck constant makes this possible by enforcing quantization at a deep level while allowing fields to evolve smoothly at larger scales. As you sit with these ideas, imagine that every beam of sunlight, every reflection on water, and every faint glow from a distant star is shaped by the Planck constant. The warmth that reaches your skin, the colors that fill your vision, and the signals that travel across space to your eyes all arise from the same dual character of light. And because light interacts with everything, atoms, molecules, empty space, its quantum nature permeates the universe. There is a quiet comfort in recognizing that the universe expresses itself in both continuity and discreteness, in waves that spread and particles that arrive with certainty. Just as life contains both fluid moments and abrupt changes, the cosmos itself holds both at once. And perhaps as you consider this delicate balance, you can feel a moment of connection to the broader universe, one where every photon, from the smallest spark to the grandest star, carries a whisper of the same quantum rules that shape your own existence. Chapter 6: How the Planck constant shapes the structure of matter. The familiar solidity of the world belies the strangeness of the forces that hold it together. When you rest your hand on a table, it feels firm, immovable, continuous. When you look at a stone, a metal beam, or a grain of sand, you see stable, enduring objects. Yet none of these forms of matter would exist without the quantum principles governed by the Planck constant. The way atoms bind, the way electrons arrange themselves in shells, the way molecules form complex structures, and the way matter resists compression all trace back to the quantization dictated by this constant. Without it, matter would either collapse into dense, structureless clumps or blow apart under unrestrained forces. The Planck constant provides the scale that allows matter to be stable, patterned, and richly varied. To understand how deeply this constant shapes matter, one must first recognize that electrons within atoms do not orbit the nucleus like planets around a star. Instead, the electrons exist as quantum waves, described by standing patterns that fill space around the nucleus. These standing waves occupy discrete energy levels, quantized states, and the spacing of these levels is set by the Planck constant. If this constant had a different value, the energy spectrum of the atom would change. The sizes of atomic shells, the spacing between orbitals, and the binding strength of electrons would all be transformed. Because atoms are the building blocks of clouds, rocks, DNA, stars, and every composite material, the structure of the entire universe depends critically on the value of this constant. The idea that electrons behave as waves might seem abstract, but it becomes clear when we consider the consequences of restricting electrons to quantized states. Electrons are not free to choose any orbit or any energy. They must occupy states whose wave patterns fit around the nucleus in precise ways. This requirement prevents electrons from collapsing into the nucleus. If they were classical particles, attracted strongly by the positive nucleus, they would lose energy as they spiraled inward, emitting radiation until they finally merged with the nucleus. But quantum mechanics forbids this. The Planck constant sets a minimum spread of the electron's wave, preventing it from localizing too precisely. This minimum spread also ensures that the electron retains a finite kinetic energy even in the lowest state. The result is a stable atom, with the electron's wave extended far enough to avoid collapse, but bound closely enough to the nucleus to form a compact structure. Stability of this kind is not a trivial feature of the universe. It requires a delicate balance between the wave nature of matter and the forces that act within the atom. The Planck constant defines that balance. If the constant were much larger, the wave behavior would dominate, spreading electrons so widely that atoms would be extremely diffuse and chemical bonds weak. If it were far smaller, the wave effects would be minimal, and electrons might collapse into nuclei or bind with excessive strength, making chemistry unrecognizable. The constant thus sets the scale for the entire periodic table. The patterns of electron shells, the geometries of molecules, and the richness of chemical reactions all follow from the structure of quantum states built around this constant. This influence extends beyond atoms into the formation of molecules. When two atoms approach one another, their electron waves overlap. Depending on the nature of this overlap, electrons may lower their energy by occupying shared states between the atoms. This is the quantum origin of the chemical bond. In covalent bonding, electron pairs are shared in specific spatial patterns. In ionic bonding, electrons shift from one atom to another. In metallic bonding, electrons flow more freely among many atoms. But in every case, the binding depends on the quantized structure of electronic energy levels, and those energy levels depend on the Planck constant. Without quantization, the distinction between stable and unstable molecular configurations would blur. Molecules would have no preferred shapes, no consistent bond lengths, and no robust structures. The chemistry that supports life, planetary atmospheres, and complex materials would simply not exist. Matter's resistance to compression also traces back to the Planck constant. In a material like steel or diamond, atoms are packed into regular arrays. When you try to compress such a material, electrons in adjacent atoms are forced closer together. But electrons, being quantum waves, obey the Pauli exclusion principle, which prevents identical electrons from occupying the same quantum state. This exclusion, combined with the quantized energy structure of matter, generates a pressure, what physicists call degeneracy pressure, that resists compression. Without the Planck constant setting the scale of electron energies, this pressure would vanish or behave differently. Stars would collapse more easily. Planetary materials would not maintain their structure. Even something as mundane as the rigidity of wood or the crunch of gravel underfoot ultimately arises from the quantum mechanical rules that prevent electrons from all occupying the same low-energy states. At extremely high densities, such as those found in white dwarf stars, degeneracy pressure takes on an even more dramatic role. In these stellar remnants, matter is compressed to enormous densities, but does not collapse into a black hole, because the quantized nature of electrons resists further compression. The sheer existence of these stars, the glowing cinders of once active suns, reflects the influence of the Planck constant at cosmic scales. If the constant had a different value, the balance between gravitational collapse and quantum pressure would shift, altering the evolution of stars and the makeup of the universe. In neutron stars, a similar quantum pressure occurs at an even deeper level, governed by the behavior of neutrons. But once again, this behavior is anchored in the quantized structure of fundamental particles. The Planck constant also governs the behavior of electrons in solids. In materials such as semiconductors, the way electrons move through the lattice determines their electrical and thermal properties. The quantized nature of electrons within the periodic potentials of crystals leads to the formation of energy bands and band gaps. These bands explain why some materials conduct electricity, others insulate, and still others behave as semiconductors, essential components in modern electronics. The precise spacing of these bands is sensitive to the Planck constant. A world with a significantly different value for this constant might lack the electronic properties needed for computation, communication, and many of the technologies that define modern civilization. Even the color of materials depends on the Planck constant. When light interacts with matter, electrons absorb or emit photons only when the photon's energy matches the difference between quantized electronic levels. The colors of pigments, the transparency of glass, the sheen of metals, all arise from how electrons respond to light of different frequencies. These responses are anchored in the quantized structure of atoms and molecules. If energy came in continuous amounts, matter would absorb or emit light in broad, undefined ranges, and color would have no meaning in the way we recognize it. Vibrational and rotational movements of molecules are also quantized. The frequencies at which molecules vibrate determine how they absorb infrared radiation. These vibrational modes affect everything from the greenhouse effect in planetary atmospheres to the functioning of enzymes in living cells. The Planck constant sets the scale of these energy differences, linking quantum mechanics to thermodynamics, biology, and planetary climate. In the vast web of physical phenomena, the constant appears not as an isolated number, but as a foundational parameter shaping the behavior of systems across many orders of magnitude. When matter interacts with light, the relationship between energy and frequency once again points back to the Planck constant. In atomic clocks, for example, the frequency of radiation emitted by electrons transitioning between specific energy levels provides an extraordinary standard of time. The precision of these clocks arises from the stability of quantized energy differences. Because the Planck constant controls these differences, it indirectly defines the measurement of time itself. Thus, the tick of the most accurate clocks we can build is connected to the same constant that determines the scale of atoms. All these aspects, atomic structure, molecular bonding, electronic behavior, material strength, stellar evolution, and timekeeping, demonstrate how deeply matter depends on quantum rules. The Planck constant sets the scale for those rules. It ensures that particles behave like waves at small scales, that energy is quantized, and that matter cannot collapse or expand arbitrarily. It is a quiet architect of reality, hidden in the mathematical description of nature, yet present in every familiar object we touch. As you let these ideas settle, consider the astonishing interconnectedness of the world. The solidity of a stone, the warmth of sunlight on your skin, the sparkle of a mineral, the resonance of a musical instrument, all emerge from the quantized structure of matter shaped by the Planck constant. You are built from atoms that obey these same laws, held together by the same quantized forces, resonating at scales far beneath awareness, yet essential to your existence. And perhaps, as you breathe and let this knowledge drift through your thoughts, you may feel a quiet sense of belonging. The constant that shapes the stability of matter also shapes you. It binds stars and cells, planets and memory, existence itself into patterns that endure. You are part of that pattern, held gently within the same quantum rules that have governed the universe since its beginning, a brief and luminous expression of the deeper order woven into nature. Chapter 7. Planck's constant and the fabric of empty space. When we speak of space, we often imagine an empty, silent backdrop, a vast nothingness stretching between stars, a smooth, passive arena in which matter and energy move. Classical physics reinforce this intuition, treating the vacuum as the absence of substance, a zero baseline against which meaningful phenomena unfold. But quantum theory paints a radically different picture. According to modern physics, the vacuum is not empty. It is an active, restless medium shaped by the Planck constant. Even when devoid of particles, fields fluctuate. Energy appears and vanishes. Virtual particles flicker in and out of existence. The Planck constant determines the scale of these fluctuations, setting the minimum amount of energy the vacuum must contain. Instead of void, space becomes a dynamic fabric filled with ceaseless quantum activity. To understand how the Planck constant connects to this behavior, one must revisit the idea that the quantum systems cannot be completely at rest. In classical physics, a pendulum can come to a stop, a spring can remain motionless, and an electromagnetic field can settle into perfect stillness. But quantum mechanics disallows perfect stillness. It demands that every field, every mode of vibration, must retain a small but irreducible energy, a zero-point energy, even when no particles occupy it. This energy is not a removable feature of the theory. It arises directly from the quantization enforced by the Planck constant. The constant sets the scale for the lowest energy that each mode of the electromagnetic field can possess. This zero-point energy leads to quantum fluctuations. Imagine an electromagnetic field in a region of space with no photons present. Quantum mechanics predicts that the amplitude of the field cannot be exactly zero. Instead, it fluctuates randomly, as though buffeted by an unseen wind. These fluctuations are not classical noise, but genuine physical events. They can influence the behavior of particles and fields, even though they arise from what we historically called empty space. The Planck constant dictates how large these fluctuations are. If the constant were much smaller, the vacuum would be calmer. If it were larger, the vacuum would be far more turbulent. The universe's stability depends critically on the delicate balance set by this constant. One of the most striking pieces of evidence for vacuum fluctuations comes from the interaction between neutral metal plates placed very close together. Even though they carry no electric charge and exert no classical electromagnetic force on one another, they feel a small attraction. This is due to differences in quantum fluctuations between the plates and outside them. Inside the narrow gap, only certain modes of the electromagnetic field can exist. Outside the gap, all modes are allowed. The imbalance creates a net force that pushes the plates together. This effect cannot be explained without acknowledging that the vacuum itself contains energy scaled by the Planck constant. Quantum fluctuations also affect atomic and molecular behavior. In atoms, electrons experience forces not only from the nucleus, but from the restless electromagnetic field surrounding them. These interactions slightly shift the energy levels of the electrons. For hydrogen, these shifts produce a subtle change in the spectral lines emitted by the atom, a phenomenon that can be measured with extraordinary precision. The existence of such tiny shifts confirms that the vacuum, even when stripped of all real particles, is not a silent stage but an active participant in physical processes. The Planck constant also shapes the behavior of fields in high-energy environments. In the early universe, when temperatures were far higher than in any modern environment, quantum fields fluctuated violently. These fluctuations seeded the density variations that later grew into galaxies and cosmic structures. Without them, the universe would be too smooth for gravitational collapse to initiate star formation. The structure of the cosmos, its clusters of galaxies, its filaments of matter, its immense voids, traces back to quantum fluctuations magnified by cosmic expansion. The Planck constant set the scale for these initial perturbations. In this sense, the constant played a role in determining the grand design of the universe. Empty space also influences forces. In quantum electrodynamics, the force between charged particles arises partly from the exchange of virtual photons, excitations of the electromagnetic field that exist only fleetingly. The Planck constant determines how these virtual excitations behave, shaping the strength of electromagnetic interactions. If the constant were even slightly different, the balance of forces could shift dramatically. Atoms might not hold together, or chemical reactions might not proceed in useful ways. Stars might fuse elements differently, and the evolution of complex structures might be impossible. The vacuum structure becomes even more intricate when considering quantum fields beyond electromagnetism. All fundamental forces have associated fields that fluctuate. Even in their lowest energy state, they are stirred by the same quantum rules. Particles such as electrons, quarks, and neutrinos arise as excitations of these fields. The Planck constant defines the quantization rules for these excitations. Without quantization, these fields would behave classically and would not produce discrete particles. The existence of matter itself, electrons that form atoms, quarks that form protons and neutrons, depends on the Planck constant establishing the relationship between field fluctuations and particle creation. Gravity, too, may arise from quantum fluctuations at extremely small scales, although a complete theory of quantum gravity has yet to be confirmed. Some theories propose that space-time itself is subject to quantum uncertainty, fluctuating on scales defined by combinations of the Planck constant, the gravitational constant, and the speed of light. At unimaginably tiny distances, space-time might not be smooth, but instead composed of fluctuating geometries, foamy structures, or discrete units. While these ideas remain speculative, they all rely on the Planck constant as a defining element of the quantum structure of the vacuum. Zero-point energy, the energy of the vacuum, is also connected to the expansion of the universe. In modern cosmology, the accelerated expansion observed today is attributed to dark energy, an enigmatic form of energy permeating space uniformly. Some interpretations suggest that dark energy is related to the vacuum energy predicted by quantum field theory, though the comparison between theoretical predictions and observations is not yet resolved. Regardless, the possibility that the fabric of space itself contains energy capable of influencing the cosmic expansion underscores the profound connection between the Planck constant and the large-scale behavior of the cosmos. The vacuum's influence extends into technological realms as well. Quantum fluctuations contribute to phenomena like superconductivity and superfluidity. In superconductors, electrons pair up and move collectively through the material without resistance, a behavior deeply rooted in the quantum structure of the underlying fields. These behaviors depend critically on the Planck constant because they rely on coherent quantum states that would be impossible if energy levels were continuous. The same principle applies to superfluid helium, which flows without viscosity due to quantum effects, manifesting on macroscopic scales. Even the stability of lasers, atomic clocks, and quantum communication devices relies on the vacuum behaving according to the quantization rules set by the constant. Seen this way, the vacuum ceases to be a background. It becomes a fundamental component of the physical world, an invisible field that shapes matter, energy, and cosmic evolution. Its fluctuations influence chemical bonds, nuclear forces, and the propagation of light. The Planck constant acts as the metronome of this hidden activity, setting the tiniest pulses and whispering constraints that ripple outward into every structure the universe has ever formed. Reflecting on this brings a subtle sense of wonder. What appears empty is not empty. What seems still is not still. Beneath the silence of space lies a restless quantum sea, vibrating with possibilities, anchored by a constant so small it cannot be sensed directly, yet so essential that reality itself depends on it. As you imagine the vacuum stretching beyond stars, galaxies, and the visible universe, you might feel a quiet connection to that deeper fabric. Every moment of your existence takes place within this shimmering field. Every atom in your body is surrounded by it, shaped by it, and sustained by it. And perhaps in the soft rhythm of your breath, you can sense a distant echo of those fluctuations. The quiet truth that even emptiness is alive with motion, and that you too are a brief, luminous fluctuation in a universe far larger and more intricate than it first appears. Chapter 8. The Cosmic Implications, from Stars to the Big Bang. The Planck constant is often introduced as a microscopic parameter, a tiny number that governs the quantization of energy at the scale of atoms and particles. Yet its influence stretches far beyond the quantum world we usually associate with electrons and photons. It shapes the physics of stars, determines the processes that power galaxies, and sets the earliest conditions from which the universe emerged. From the temperature profile of the cosmic microwave background to the behavior of matter in stellar cores, the Planck constant is woven through the cosmos at every level. Its value influences how stars shine, how elements form, and how the universe evolved from its earliest moments. Without this constant, the cosmic landscape would look nothing like it does today. To see this connection, begin with the life of a star. Stars shine because they produce energy in their cores through nuclear fusion. In the heart of a young star, hydrogen nuclei must overcome their electric repulsion to merge into helium. Classical physics predicts that, given the typical temperatures of stellar cores, hydrogen nuclei should rarely, if ever, fuse. The temperatures are high, but the repulsive forces between positively charged nuclei are severe. Yet fusion occurs regularly enough to power stars for billions of years. The reason lies in quantum tunneling, a phenomenon governed by the Planck constant. Quantum tunneling allows particles to pass through energy barriers that would be insurmountable in classical physics. In the context of stars, it enables hydrogen nuclei to fuse even when their thermal energy is insufficient to overcome the repulsive barrier. The tunneling probability depends on the Planck constant. If the constant were much smaller, tunneling would be far less effective, and stars would require much higher temperatures to ignite. Many stars, including the Sun, might never have formed stable burning phases. Conversely, if the constant were larger, fusion would occur much more readily, making stars burn too quickly and too brightly, shortening their lifetimes and altering their structure. The long-term stability of stars and the existence of habitable environments around them is possible only because the Planck constant strikes a delicate balance in the behavior of tunneling. In addition to enabling fusion, quantum mechanics shapes how energy is transported inside stars. Photons created in fusion reactions undergo countless interactions as they travel outward from the stellar core. Along the way, processes such as absorption, re-emission, and scattering depend on the quantized structure of atomic energy levels. This structure determines how efficiently stars can transport energy and thus influences their temperature gradients, luminosity, and size. Even the spectral light we observe from stars arises from photons emitted through quantized transitions in atoms. The colors of starlight, the absorption bands that reveal stellar composition, and the patterns astronomers decode all exist because atomic energy levels are discrete, a direct consequence of the Planck constant. The interior structure of stars also depends on quantum effects in dense matter. In white dwarf stars, for example, the collapse of the stellar core is halted by electron degeneracy pressure, a quantum mechanical effect that arises from the wave nature of electrons and the quantization of their energy states. Without the Planck constant fixing the scale of these energies, such degeneracy pressure would not exist or would behave differently. White dwarfs might collapse further into neutron stars or black holes, or they might never form as stable remnants at all. The entire evolution of stars from birth to death is tied intimately to the quantum principles encoded by the Planck constant. Beyond individual stars, the Planck constant influences the formation of elements in the universe. During stellar fusion and supernova explosions, nuclear reactions produce elements heavier than helium. These reactions depend on quantized energy levels within nuclei and the probabilities of tunneling and particle interactions. Without the precise behavior dictated by the Planck constant, the periodic table would be altered. Some elements might never form, others might be unstable. The chemical diversity required for planets, life, and complex molecules depends on nuclear processes whose rates and pathways follow quantum rules. But the influence of the Planck constant extends even deeper in time. To understand the earliest universe, one must examine the Planck era, the brief moment following the beginning of cosmic expansion when densities and temperatures were so extreme that classical descriptions of space-time fail. Although we do not yet possess a full theory of quantum gravity, theoretical models suggest that, in this era, space-time itself was subject to quantum fluctuations controlled by combinations of fundamental constants, including the Planck constant. In this region, the fabric of the universe may not have been a smooth continuum, but a foamy, fluctuating structure governed by quantum uncertainty. As the universe expanded and cooled, these fluctuations left imprints on the distribution of matter and energy. Slight differences in density eventually grew into the large-scale cosmic structures we see today: galaxies, clusters, and cosmic filaments. These initial fluctuations were tiny, but their amplification over cosmic time sculpted the visible architecture of the universe. The amplitude and character of these fluctuations depend on the quantized behavior of fields in the early universe. The Planck constant determines how these fields fluctuate, how strongly they couple, and how they generate perturbations. Thus, the universe's large-scale structure is tied to microscopic quantum principles embedded in this constant. The cosmic microwave background, a faint glow from the early universe, provides further evidence of the Planck constant's influence on cosmic evolution. The tiny temperature variations observed in this background correspond to regions where quantum fluctuations once rippled through the primordial plasma. These fluctuations later became the seeds of galaxies and clusters. The patterns of these variations, their statistical distribution, their scale, their uniformity, reflect the quantum processes that operated when the universe was still very young. Observations confirm that these fluctuations match predictions from quantum field theory embedded in a growing space-time. The Planck constant, which appears throughout quantum field equations, thus plays a quiet role in shaping the observable form of the cosmos. As the universe expanded through its first fractions of a second, several transitions occurred, each governed by physics that includes quantum effects tied to the Planck constant. When the universe cooled enough for quarks to bind into protons and neutrons, quantized strong interactions determine the stability of these particles. Later, when electrons combined with nuclei to form neutral atoms, the quantized structure of hydrogen and helium shaped the interaction between matter and radiation. These events allowed light to decouple from matter, creating the cosmic microwave background. Each step in this chain, particle formation, atomic structure, photon decoupling, reflects a layer of physics bound together by quantization. Even gravity at cosmic scales feels the influence of quantum rules. While gravity is described classically by general relativity, many cosmological processes require input from quantum field theory. For example, the inflationary theory of the early universe uses quantum fluctuations to explain the uniformity and structure we observe today. Although inflation remains an area of active research, almost all models rely on the idea that vacuum fluctuations, shaped by the Planck constant, were stretched to astronomical scales, imprinting patterns across the universe. These stretched fluctuations form a bridge between microscopic quantum behavior and macroscopic cosmic structure. The Planck constant also influences the cosmic energy budget. Processes such as black hole evaporation rely on quantum principles. At the edge of a black hole's event horizon, quantum fluctuations may lead to the emission of radiation. This process, although extremely slow for large black holes, is determined by the same quantized behavior that governs atomic transitions. If the Planck constant had a different value, the rate of such radiation would change. The lifetimes of black holes, the birth of particle pairs near horizons, and the energy carried away depend on this fundamental constant. In summary, the Planck constant is far more than a parameter for small-scale physics. It shapes the cosmic furnace of stars, the pathways of stellar evolution, the nuclear synthesis of elements, and the earliest moments of the universe's existence. It guides the fluctuations that seeded galaxies and influences the interactions that produce starlight itself. The universe is not merely large, it is deeply quantum. Its structure, its history, and its future all trace back to quantized rules that operate far below the scale of human perception, bound together by a constant so small that it seems almost intangible. As you reflect on this, consider how astonishing it is that the vastness of the cosmos depends on something so subtle. Galaxies stretching across cosmic distances, stars burning for billions of years, planets forming from swirling disks of dust, and the quiet, persistent background glow of the early universe all arise from the microscopic laws that the Planck constant enforces. In that delicate interplay between the tiny and the immense lies one of the most beautiful truths of physics. And perhaps, as you let these ideas settle, you may feel a sense of connection to the deeper rhythms of the universe. You live in a cosmos shaped by quantum flickers that gave birth to galaxies. The warmth of the sun, the stability of matter, and the existence of life all depend on that subtle constant. You too are part of a cosmic story that began in those early quantum fluctuations, a brief consciousness emerging from an ancient sequence of events, held together by the quiet order woven into the fabric of the universe. Chapter 9. Searching for quantum gravity, where the Planck scale leads. At everyday scales, gravity feels simple, almost familiar. It pulls objects toward the ground, shapes the motion of planets, and guides the evolution of stars and galaxies. Einstein's general relativity provides a beautiful description of this force, not as a pull, but as the curvature of space-time. According to this theory, mass and energy shape the geometry of the universe, and that geometry dictates how objects move. On cosmic scales, general relativity is astonishingly successful. It predicts the bending of starlight, the slow dance of binary pulsars, the expansion of the cosmos, and the ripples of gravitational waves. But at the smallest scales, at distances comparable to the Planck length, Einstein's smooth fabric of space-time cannot remain smooth. Quantum mechanics insists that nothing can have perfectly well-defined values, and that includes space-time itself. At the Planck scale, the uncertainty in energy becomes so large and the localization of particles so extreme that the gravitational field must fluctuate violently. The smooth geometry of relativity dissolves into something far more irregular. The Planck constant, combined with the gravitational constant and the speed of light, defines this boundary. Below this scale, our classical picture of spacetime fails, and a new theory must take over, a theory of quantum gravity. Quantum gravity is not simply the quantum version of gravity. It is a radically new framework in which the concepts of space, time, and geometry emerge from deeper quantum principles. Developing such a theory has become one of the central challenges of modern physics. For decades, physicists have tried to unify general relativity and quantum mechanics, but these two theories treat the world in fundamentally different ways. Relativity is geometric, continuous, and deterministic at large scales. Quantum mechanics is probabilistic, discrete, and fundamentally uncertain. Where relativity bends spacetime smoothly, quantum mechanics allows even the vacuum to fluctuate. Bringing these two descriptions into harmony is extraordinarily difficult. The need for quantum gravity becomes evident in extreme conditions. Consider a black hole. General relativity predicts that inside a black hole lies a singularity, a point where density and curvature become infinite. But infinities are usually signs that a theory has reached its limits. In the intense gravitational field near a singularity, quantum effects must become important. Similarly, the beginning of the universe presents a situation in which the density and temperature were so high that quantum fluctuations of spacetime would have been significant. Classical relativity cannot describe these conditions fully. A consistent theory of quantum gravity is required to explain what happened during the earliest moments of the cosmos. One approach to quantum gravity comes from applying the principles of quantum field theory directly to the gravitational field. In quantum field theory, each force of nature is associated with a field whose quanta appear as particles. For electromagnetism, the quanta are photons. For the strong nuclear force, they are gluons. If gravity were treated in the same way, the force would be carried by hypothetical particles known as gravitons. These particles would be extremely light and interact very weakly with matter. Although no experiment has detected them, the graviton framework follows naturally from quantizing the gravitational field. Yet this simple idea encounters difficulties. When physicists attempt to calculate gravitational interactions at very high energies using this approach, the equations produce divergences that cannot be removed in the usual way. The theory seems incomplete. Gravity, as Einstein described it, may not be well suited to being quantized in the same manner as other forces. The structure of space-time itself may require a more fundamental revision. This need for revision led to the development of string theory. In string theory, the fundamental objects are not point particles but tiny vibrating strings. Each mode of vibration corresponds to a particle with specific properties, including mass and charge. Remarkably, one of the vibration modes of a string behaves like a graviton. This means that gravity emerges naturally from string theory without needing to be added by hand. Because strings are extended objects rather than points, the problematic infinities that appear when point particles interact at arbitrarily short distances are smoothed out. The Planck length becomes the smallest meaningful scale, below which space cannot be probed because attempting to do so would excite new vibrational modes of the string rather than reveal smaller structure. String theory also suggests that space-time may have more than the familiar 3 spatial dimensions. These extra dimensions are thought to be compactified, curled up so tightly that they cannot be seen at ordinary scales. The geometry of these hidden dimensions influences the properties of particles and forces in our observable universe. Although string theory remains mathematically rich and conceptually compelling, it has yet to produce definitive experimental predictions. Still, it provides one of the most fully developed frameworks for unifying quantum mechanics and gravity. Another major approach to quantum gravity is loop quantum gravity. This theory begins from a different starting point. Instead of treating particles as strings, it attempts to quantize space-time directly. In loop quantum gravity, space is composed of tiny discrete loops woven into a network, forming a kind of quantum fabric. Areas and volumes come in quantized units, meaning that space cannot be subdivided indefinitely. At large scales, this network approximates smooth geometry, but at the Planck scale it becomes granular. Loop quantum gravity also suggests that the singularities predicted by general relativity, such as those inside black holes or at the beginning of the universe, may not exist. Instead, space-time could undergo a transition, like a bounce, avoiding the infinities that plague classical theories. Both string theory and loop quantum gravity attempt to describe the Planck scale behavior of space-time, yet they are built on very different mathematical foundations. Each offers insights, but neither is complete. Other approaches exist as well. Some theories treat space-time as a causal network of discrete events. Others propose that gravity may be an emergent phenomenon, arising not from a fundamental force, but from the statistical behavior of microscopic degrees of freedom. Still others explore the idea that space-time geometry can be encoded in patterns of quantum entanglement. These ideas suggest that space might not be a basic ingredient of the universe, but a consequence of how quantum information is organized. Measurements involving black holes have become especially important in this search. Theoretical studies of black hole evaporation show that black holes radiate energy due to quantum effects near the event horizon. This radiation implies that black holes lose mass over time. Yet this process raises deep questions about the fate of information. If a black hole evaporates completely, what happens to the information contained within? Quantum mechanics insists that information cannot be destroyed. Resolving this paradox requires a quantum theory of spacetime that can describe the interior of black holes and their evaporation consistently. Recent ideas suggest a surprising possibility. Spacetime geometry may be deeply connected to quantum entanglement. Entangled particles share correlations that persist even when separated. Some researchers propose that these correlations might be responsible for stitching spacetime together. In this view, the smooth geometry of space is a large-scale manifestation of countless entangled quantum states. If so, then the Planck constant, which governs quantum behavior, indirectly shapes the geometry of the universe. Gravity, in this picture, could arise not from curvature but from the flow of quantum information. While speculative, these ideas highlight the growing belief that gravity, quantum mechanics, and information theory may be intertwined at a fundamental level. Despite the progress of many decades, no single theory of quantum gravity has yet emerged as definitive. Experiments are challenging because the Planck scale lies far beyond the reach of current technology. But indirect clues may arise from observations of black holes merging, gravitational waves interacting with extreme environments, and the behavior of high-energy cosmic particles. The future of quantum gravity research may involve combining theoretical insight with precision cosmology, using the universe itself as a laboratory. The search for quantum gravity reflects a deeper human desire to understand the foundation of reality. We know that classical spacetime is not the final word. We know that quantum mechanics, though astonishingly accurate, must ultimately be reconciled with gravity. And we know that the Planck constant marks the boundary where this reconciliation becomes unavoidable. The theories we build to cross that boundary will reshape our understanding of time, space, and causality. As you let these ideas settle, you might notice a quiet feeling beneath the scientific complexity. The universe, at its deepest level, remains unfinished in our understanding. The Planck scale is not merely a limit, it is an invitation. It calls us toward a future where the fabric of reality, the geometry of space, the flow of time, the nature of information, may reveal a unity we have not yet seen. You, like every conscious being, live suspended between the large and the small, between galaxies shaped by gravity and atoms shaped by quantum rules. And perhaps, as you breathe and reflect, you can feel a quiet sense of belonging in the midst of that mystery. A reminder that understanding the universe is also a way of understanding your place within it. Chapter 10. The meaning of the smallest number. Why h exists at all. Among all the constants that shape the physical world, the Planck constant stands apart in its strangeness. It is extraordinarily small, yet this tiny value governs the scale of quantum behavior across the universe. It appears in every equation of quantum mechanics. It sets the size of energy quanta, the wavelength of matter waves, the structure of atoms, the behavior of electromagnetic fields, and the fluctuations of empty space. Without it, none of the familiar features of matter or radiation would exist. But this raises a profound question. Why does the universe contain such a constant at all? What does it mean, physically or conceptually, for the universe to have a smallest step, a minimum action? Why does reality choose this discrete architecture and not another? These questions go beyond the mechanics of physics. They touch the foundations of what it means for something to exist and how fundamental laws arise from deeper principles. To search for meaning in the Planck constant is to ask why the universe is quantized, why continuity gives way to discreteness, and why the smallest allowable scale has precisely the value it does. The first essential point is that the Planck constant emerges naturally from the structure of wave mechanics. Quantum mechanics treats particles not as tiny marbles, but as waves of probability, waves that can interfere, diffract, and form standing structures. In this framework, the energy of a system is intimately linked to the frequency of its wave behavior. The Planck constant provides the bridge between these two quantities. It determines how much energy corresponds to a given oscillation. Without this connection, wave-like and particle-like behavior could not be unified. Light would not behave as both particle and wave. Electrons would not form standing wave patterns around nuclei. Matter waves would not exist. In a sense, the constant is the conversion factor that allows the universe to support wave-like matter. If the constant were absent, there would be no quantization of energy levels, no atomic stability, and no structured matter. Everything would blur into a continuous smear of energy. The Planck constant preserves structure by limiting how small an action can be, preventing systems from collapsing into arbitrarily precise configurations, and ensuring that waves cannot have arbitrarily high frequencies without corresponding energy costs. This limitation gives rise to the stability of atoms and the persistence of matter. But why should the universe be built this way? One answer is that quantization may be a consequence of the deeper symmetries of the physical world. Many physical laws arise from symmetry, the invariance of nature under translation, rotation, or other transformations. In quantum mechanics, these symmetries translate into conserved quantities, such as energy and momentum. The Planck constant appears naturally when expressing these relationships. It may not be arbitrary, but the natural scale at which these symmetries and conservation laws coexist consistently with the probabilistic nature of quantum mechanics. Another perspective arises from information theory. In some modern interpretations, the Planck constant defines the fundamental resolution of information in the universe. Just as a digital image has a smallest pixel size, quantum mechanics has a smallest resolvable unit of action. This prevents infinite precision. It forces limits on how much information can be extracted about a particle's position and momentum. This limit is not a flaw, but a feature that avoids contradictions within the theory. If one could measure position and momentum with infinite precision, many of the foundational principles of quantum theory would break down. The Planck constant thus encodes a minimum uncertainty, preserving the internal consistency of quantum physics. The value of the constant also matters. It is not enough that the universe is quantized. It must be quantized at precisely the scale the Planck constant provides. A universe with a much larger constant would be wildly unstable. Electrons would spread out over vast regions, atoms would be diffuse, and chemical bonds would be weak or impossible. Conversely, a universe with a much smaller constant would allow electrons to be tightly packed into the nucleus, eliminating the structured energy levels that give rise to chemistry. Stars would burn differently. Molecules would not be able to form complex shapes. Life, as we understand it, would be unimaginable. Thus, the Planck constant is not merely small, it is appropriately small. It sits within a range that allows matter to exist, stars to shine, and complexity to evolve. Some physicists view this as a consequence of deeper physical laws yet to be discovered. Others see it as a reflection of anthropic reasoning, the idea that the universe must have a value compatible with observers because observers exist to measure it. But neither perspective diminishes the fact that the Planck constant provides a delicate and necessary foundation for the universe's structure. A deeper question emerges: is the Planck constant truly fundamental, or could it arise from something even more basic? Many theories of quantum gravity explore this. In approaches where space-time itself is quantized, the Planck constant appears as a natural measure of the smallest unit of geometry. In string theory, the constant connects the tension of vibrating strings to their quantum vibrations. In approaches where gravity emerges from quantum information, the constant may be related to the entanglement structure of space-time. In each case, the Planck constant is not merely inserted into the equations, but arises from the internal logic of the theory. This suggests that the constant may not be arbitrary. It may be a shadow of something deeper, a sign that our universe's microscopic architecture is built from discrete quantum units. The Planck constant also governs phenomena in empty space, where fluctuations correspond to real physical effects. Even when matter is absent, the vacuum never sits completely still. Its fluctuations have energy, momentum, and measurable influence. That the vacuum possesses such restless activity is another reflection of the Planck constant's meaning. It tells us that the universe is active even in its lowest energy state. There is no perfect stillness, no complete calm. Movement and uncertainty are baked into the foundation of reality. For all of its profound implications, the Planck constant remains experimentally simple to measure. Modern techniques tie the definition of mass to fundamental constants, and the Planck constant is a reference point in this system. Measurements of atomic transitions, electrical resistance, and photon emission all rely on this constant and confirm its role over and over. It appears with absolute regularity, a silent anchor linking countless experiments across physics. This consistency reinforces the belief that the constant is truly fundamental. Reflecting on the meaning of the Planck constant brings a deeper appreciation for the elegance of the universe's design. The constant is a hinge between wave and particle, between uncertainty and structure, between discreteness and continuity. It governs the scale of the microscopic world while influencing the stability of the macroscopic one. It sets the architecture for matter, light, and space-time. It shapes the vacuum and the behavior of stars. It binds together the smallest and the largest, the invisible and the immense. As you let these ideas settle in your mind, it becomes clear that the Planck constant is not just a number in a textbook. It is a quiet principle woven through existence. It whispers the rules by which atoms hold together, by which stars ignite, and by which the early universe evolved. And it also whispers something more subtle, that the universe, for all its vastness, is structured from limits, boundaries, and discrete steps. Perhaps as you reflect on this smallest constant, you may feel a sense of calm connection to the larger cosmic story. You, like every molecule in your body, are shaped by the value of this tiny constant. You are part of a universe where order arises from the smallest scale, where uncertainty becomes possibility, and where even the limits of nature carry the seeds of complexity and life. In that delicate balance, you may sense a quiet truth, that your existence, like the Planck constant itself, is both small and immeasurably significant. My friend, Thank you for spending this time with me among the laws of the universe. If you're still awake, you're welcome to stay and watch another journey through the cosmos. It's right here waiting for you. And if your eyes are closing now, then sleep gently, wander far, and dream sweetly among the stars. Good night.